In this lesson, we're going to revisit some concepts that we've looked at in previous years that we worked with in degrees, and we're going to apply them to radians. So the terminology has not changed. We know that an angle in standard position is an angle that starts on the positive x-axis and ends with the terminal arm. That angle is called the principal angle. We're going to use this little symbol to denote the principal angle, and that's called alpha. The acute angle between the terminal arm and the x-axis, that's called the related acute angle, and we've seen that before. We're going to call that beta. So alpha will be our principal angle, beta will be our related acute angle. And we remember that coterminal angles are angles that look the same. They have the exact same terminal arm, but they have different measures. So for example, 360 degrees would be all the way around a circle. 720 degrees would look the same, would have the same terminal arm, but has a different angle measure. So let's try sketching these angles, and we're also asked to determine the related acute angle and one coterminal angle. So it's going to be tempting, but let's resist the urge of translating that into degrees. So we could pop 180 into there and multiply 5 times 180 divided by 4 and work in degrees, but let's wrap our minds around what this means in terms of radians. So we know what pi radians is. That's just going to be half of our circle. And 5 over 4 pi's means 5/4 of pi, and we know 1/4 would be here, 2/4 is a half pi, 3/4 would be here, 4/4 would be here. That means 5/4 must be right in the middle in our quadrant number 3. So that must be 5 over 4 pi radians. So now let's label it. So this is going to be our alpha. Alpha is going to equal 5 pi over 4 radians. So now let's figure out what's the measure of beta. So we know the related acute angle is always the angle between, the x-axis and our terminal arm. So here's our beta measure. The question is, what is beta? Well, we know that the measure in radians from here to here is 5 pi over 4. We know the measure from here to here is pi radians. So what's left over? We can figure out beta by just taking 5 pi over 4 and subtracting pi. So one more time, we know that this measure is 5 pi over 4 radians. From here to here is just pi. What's the little bit left over? So let's take 5 pi over 4, subtract pi. So really quickly we're going to make an equivalent denominators. So we're going to multiply by 4, multiply by 4. So on the top we have 5 pi minus 4 pi. That's just going to be pi over 4. And that makes sense. 1/4 of a pi should be left over. So our beta measure is pi over 4 radians. Now let's make a coterminal angle. Remember, coterminal angles look exactly the same. So it's going to have the same terminal arm, but their measures are different. Well, if this is 5 pi over 4, what if we just add another 2 pi to this terminal arm? So we end up right back where we started. That would give us a different angle measure. So if we take our angle measure of 5 pi over 4, add another 2 pi, it's going to have the same terminal arm, but it's going to have a different measure, and that's what a coterminal angle is. So another way we could do it is we could subtract 2 pi, go the other way, and get a negative angle. That could also work. So the easiest way to come up with a coterminal angle is just add 2 pi or subtract 2 pi. So let's call our coterminal angle theta, because we haven't used theta yet. So let's say theta, our coterminal angle, is equal 5 pi over 4, but let's add 2 pi. Again, you could also subtract. So theta is going to equal 5, let's make this in over 1, and we're going to multiply by 4 and multiply by 4, so that we have 5 pi plus 8 pi, which gives us 13 pi over 4. So there we have a coterminal angle. Let's try the next guy. So here's our radian measure, 17 pi over 6. Again, we're resisting the temptation of changing degrees. Let's just think about this in terms of radians. So 7 pi over 6 radians, 17 pi over 6 radians. So that's 17/6 of a pi. So we know 17 divided by 6 is greater than 2. Therefore, if it's 17 over 6 is greater than 2, that means it's greater than 2 pi, which means we are going around the circle more than once and a little bit more. So 17 divided by 6 is actually 2.83. So we're going 0.83 more. So let's just figure out how many 6 we're going and where it's going to end up and what quadrant it's going to end up in. So that we know that we can count around the circle here in 6 of pi's. So if I were to take pi, which is we know here, and divide into 6, well, I would make this into 3 and this into 3, and there's our 6. So if we were to go around the circle again, just into 3, this into 3, and here we go. So we can count 6. Here's 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6, 6. So we have to count 17 6. Let's do that. Here's 6 6. Here's 12 6. We're still not there. Here's 18 6, but we need 17 6. So 17 6 must be right here. So this is our measure of 17 6 of a pi. So our angle, which is 17 pi over 6, is this guy here. That's what 17 pi over 6 is. We've gone around the circle once and come back again. So what's our principal angle? Well, the principal angle is going to be from our from the positive x-axis all the way over to our angle here. So that's going to be our alpha. What's that? Well, that's just a coterminal angle to 17 pi over 6. So instead of going around the circle and then here, how about just directly from the x-axis over to here? That's just going to be taking this angle 17 pi over 6 and subtracting 2 pi. So I can figure out what my alpha is, my angle in standard position, by just taking 17 pi over 6 and subtracting 2 pi. Quickly making our denominators the same by multiplying by 6 and multiplying by 6. We have our alpha is going to equal 17 pi minus 12 pi, which is going to be 5 pi over 6. So our alpha, measure of alpha, our principal angle, is 5 pi over 6. How about our beta? Here's our beta, our related acute angle. So that's the angle with the terminal arm, between the terminal arm and the x-axis, that makes an acute angle. So this guy, if this guy is 5 pi over 6 and the whole halfway around the circle is pi, we can just take pi, take away 5 pi over 6, and whatever's left over must be our beta angle, our related acute angle. So beta is just going to equal, start with pi, take away 5 pi over 6, and whatever's left over is going to be beta. So we're going to do pi minus 5 pi over 6. Again, we're going to make equivalent denominators, multiply by 6, multiply by 6. And that's going to give us 6 pi minus 5 pi is just going to be pi over 6. So this guy here is just pi over 6. And in this question, we've actually already come up with a coterminal angle. That was the last thing that we had to do, because we know a coterminal angle to 17 pi over 6 is just 5 pi over 6. We found this coterminal angle by subtracting 2 pi. We could have also added 2 pi to come up with another coterminal angle. Now let's look at a third example. We can see that we're given a negative radian measure. So we know that if an angle is positive, it's going to start on the positive x-axis, and we're going to twist our terminal arm or rotate our terminal arm counterclockwise around the grid. If it's negative, we're going to start on the positive x-axis and we're clockwise around the grid. So we can read this as negative 18 quarters, which means we're going to count 18 quarters around in the negative direction. Another thing we could do is we could just simplify this. Negative 18 over 4 can be further simplified into negative 9 over 2 pi. Therefore, we can also think about this as 9 halves in the negative direction. And by 9 halves, I mean 9 half pi's. So we know, again, this is pi radians, and here's another pi radian, so 2 pi radians. So if we're looking for 9 halves, well, half of a pi would be here. Another half would be here, and so on, and so on, and so on. So let's count 9 of them. So we have 1 half, 2 halves, 3 halves, 4 halves, 5 halves, 6 halves, 7 halves, 8 halves, 9 halves. So we're back down on this line down here. So let's put a line. So now we have our measure of negative 9 pi over 2. So again, we start on the positive x-axis. We worked our way around this way. Positive x-axis worked around here. This was 1 half, 2 halves, 3 halves, 4 halves, 5 halves, 6 halves, 7 halves, 8 halves. Here was 9 halves. So there was our crazy looking angle. So let's figure out what our principal angle is going to be. So our principal angle has to be positive and be between 0 and 2 pi. So here's our principal angle, alpha. And we know that this is just an angle in the unit circle that we talked about in our first lesson on radians. So we know that this is pi and this is another half pi. So it means that this is 1.5 pi, and another way to say that is 3 over 2 pi. Now we can calculate what the related acute angle is, which we can find here, or you could also argue is also here because it's equidistant, which is true. And that's because it actually doesn't really have a related acute angle because the angle's not acute. We can see this is just half of pi radians because we know this would be pi and this is just half pi. So I don't even need to calculate it. We can just see right away that this, if we are going to give it a beta, is going to be pi over 2. And again, we've already come up with a coterminal angle to this guy, which is this one right here. So this is, these two will have the same terminal arm, but they have different angle measures. A quick refresher about trig ratios. We know that there are 6 trig ratios. We learned 3 in grade 10, sine, cos, and tan, and then we added the reciprocal ratios in grade 11, and that's cosecant, secant, and cotan. So we can remember that cosecant is just the reciprocal of sine. So it's equivalent to 1 over sine. It's just, we gave it a name. It's called cosecant. And so because it's the reciprocal of sine, all we have to do is take the sine ratio and flip it to get cosecant. And that's the same with cos and secant. Secant is just the reciprocal of cos, or 1 over cos. Therefore, we can take the ratio of cos and just flip it to get secant. And that goes the same for cotan and tan. So let's use that refresher of trigonomic ratios and solve this problem. So this one says the point 4, negative 3 lies on the terminal arm of an angle theta in standard position. Determine the exact values of all trig ratios. All means 6. So not just sine, cos, tan, but the reciprocal ones too. And the measure of the principal angle in radians to the nearest hundredth. So we see that and we know that this is probably not going to give us an angle that's on the unit circle, so we're going to have to round. So let's start by plotting that point and drawing a terminal arm. So now we've got to come up with the exact values of all the trig ratios associated with this angle. So we know that the principal angle is this guy right here. We can call that guy alpha. We don't know what that is yet. And we know the related acute angle is the angle on the inside. There it is. Okay, so what we're going to do is we're going to find all of the trig ratios associated with our acute angle, whatever that is. And then let's check the signs of sine, cos, and tan and make sure that they match what's supposed to happen in this quadrant. So what we're going to need for that is our cast rule, which we learned last year. So remember, our cast rule is a little something to help us to memorize what ratios are positive in which quadrants. So in quadrant 1, all ratios are positive. In quadrant 2, all sine ratios are positive, so sine and cosecant. In quadrant 3, tan ratios are positive, and in quadrant 4, cos ratios are positive. So we'll use our related acute angle to figure out our ratios, and then we'll use the cast rule to make sure that we have the signs right. So let's start with sine. So we know sine is opposite over hypotenuse. So this point is the point 4, negative 3. So do we know what the opposite side is and what the hypotenuse side is? Well, if this is the point 4, 3, that means that this side length over here, we'll do it in red, is 4, and this side length here is 3. So we do have the opposite side, it's 3, but we don't have the hypotenuse. So we can find the hypotenuse just by using the Pythagorean theorem. So if we do 4 squared plus 3 squared is equal to whatever our radius is squared. We can just solve that. We're going to get a radius of 5. So our radius is 5, and now we can finish off all these ratios. So sine is going to be opposite over hypotenuse, so our opposite is going to be 3 over hypotenuse, which is 5. Cos is going to be adjacent over hypotenuse, so we're going to have 4 over 5. And tan is opposite over adjacent, so we have 3 over 5. And then cotan, secant, and cosecant are just going to be reciprocals of their partner. So cosecant is just the reciprocal of sine. Secant is just the reciprocal of cos, so we're going to put 5 over 4. And cotan is the reciprocal of tan, 5 over 3. So now let's make sure that our signs are right. So using the cast rule, this is just our related acute angles, not actually our angle. It's not the principal angle alpha. Or we also denoted with theta here because that's what it gave us in the question. So this is our principal angle. So we need to make sure that these signs work for this principal angle. And the principal angle is in quadrant 4, and only cos ratios should be positive, which means that there needs to be a negative in front of sine here, a negative in front of tan, a negative in front of cosecant, and a negative in front of cotan. So the only ones that should be positive are cos and secant. So part B just asks us to find the measure of the principal angle which we've labeled alpha, in radians to the nearest hundredth. So we know we're going to have to round here. So we already have all the ratios we could possibly need. In our calculator, we don't have cosecant, secant, and a cotan, but we do have sine, cos, and tan. So let's pick one of these 3 ratios and just use sine inverse, cos inverse, or tan inverse. So if you have a choice, I usually like to choose the ratio that's positive because it's going to give you the sort of easiest number to understand what's going on. If you pick a negative number, it's not a big deal. We can still figure it out. So let's say that for B, I decide to use our ratio for sine. So in order to find our alpha or our theta, we're going to take the sine inverse of negative 3 over 5. Make sure that your calculator is in radians. So if you take the sine inverse of 3 over 5, we get negative 0.64 radians approximately. The question asks us to round it to the nearest hundredth. Okay, so does this make sense? Is this angle right here negative 0.64? That makes sense that this is negative 0.64. So that means that our related acute angle, which is beta, is positive 0.64 radians. So now let's figure out what the heck our alpha is. So it was asked us for a principal angle, which means it has to be positive in between 0 and 2 pi. So we know that the whole way around the circle is going to be 2 pi. Then if we backtrack 0.64 radians, how much is going to be left over? So our alpha is going to start with 2 pi, then we're going to radians, and we're going to subtract 0.64 radians, and what will we be left with approximately? We will have an angle measure of approximately 5.64, so I'll just put some dots here, 5.64 radians. And does this make sense? Well, we know all around a circle is 2 pi radians. That's just over 6. This is pretty close to 2 pi, so it makes sense that we're at 5.64 radians. That's also pretty close to 6. So there is our principal angle. Let's take a look at another example now. If tan of some theta, some angle, is negative 7 over 24, where we know theta is measured in radians because this is our restrictions, so it's a principal angle because it's in between 0 and 2 pi. Evaluate theta to the nearest hundredth and determine the exact ratio for sine. So here, to the nearest hundredth, this means that we are going to have to approximate this. So we're going to have to round. Determine an exact ratio for sine. Here, there should be absolutely no rounding. We should have an exact number or a ratio that we can have for sine. So let's first start off with a quick picture. So we know, the only thing we know about theta is its tan ratio. And we know its tan ratio is negative. Therefore, what quadrants must it lie in? So using the cast rule, we'll just write it out here. We know that tan can't be negative here. Tan can't be negative here either, because those were tans positive, which means that the possible values for theta must exist in the quadrant 2 and quadrant 4. Which means here are our possible measures for theta. Our theta 1 is this guy right here. That's going to be in quadrant number 2. And our theta 2 is going to be here. That's going to be in quadrant number 4. So for every solution, we're going to have 2 solutions. Again, if this restricted this between 0 and pi, our only option would be theta 1. Or if it said it had to be between pi and 2 pi, then our only option would be theta 2. But we can work with every angle from 0 to 2 pi. Therefore, we're going to have 2 solutions to this question. So now let's come up with the measures of these to the nearest hundredth. So the clue that we're given is tan, and we're giving it in ratio form, which is helpful because we know that the ratio of tan is equivalent to opposite over adjacent. So if we make our terminal arms into triangles, I'm just going to connect this guy here and connect this guy here. We can start to label these triangles. We know that the opposite sides are going to be 7, so I can put 7 here. And we know that the adjacent sides are going to be 24. And one of those has to be negative. So the first question again just asks us to evaluate theta. So we have a ratio for tan, so we can just apply tan inverse to find theta. So if I take this tan inverse of this, I'm going to get a negative angle measure. Personally, I always like to find, if I'm given a negative ratio, I always like to make it positive because that means I'm always going to be given my related acute angle measure. So I can always find the measure of the related acute angle if I take the inverse of the positive ratio that I'm given. If you were to take tan inverse of negative 7 over 24, you're just going to get a negative radian, which there's nothing wrong with that, but it's just we're always going to get something positive if we take the positive ratio. So if we take the tan inverse of positive 7 over 24, we get a radian measure of approximately 0.28. Let's take 4 decimal places. 2838 radians, and then we'll reduce to the nearest hundred at the end. So our beta measures are right in here. So there's our beta, here's our beta, they're exactly the same. So we can figure out our theta 1 by just taking pi and subtracting our beta, 0.2838. And that's because, if I want to figure out this guy here, this is pi radians, and if I just want to backtrack 0.2838 radians, I'm just going to subtract pi minus 0.2838. And we will get approximately, these are all approximate, 2.86 radians. For theta 2 now, that's in quadrant 4, right over here. So if we go all the way around, it's 2 pi, and if we backtrack that beta, backtrack 0.2838 radians, we're going to get our solution. And we get approximately 6.00 radians. So there are our approximate measures of both our thetas. So part B says determine an exact ratio for sine. Well, that's similar to the question we did before. We know that for a ratio for sine, we need opposite and hypotenuse. And we're going to come up with 2 ratios, one for theta 1, and we're also going to have another one for theta 2. The numbers in both of these ratios will be the same because they have the same related acute angle, but their sign, by sign I don't mean this sign, I mean like the plus or minus, positive or negative sign might be different depending on where it is in which quadrant it lies in. So we know sine is opposite over hypotenuse. We know the opposite side of both angles is 7. We don't know the hypotenuse. However, we can come up with it by using the Pythagorean theorem quickly. So I figured out my radius using the Pythagorean Theorem over here, and I'm going to add it to our chart or our diagram. So this is a radius of 25 even, which works out so nicely. So now we can fill in our sine ratios. So our sine of theta 1 is going to be our opposite side, which is 7, all over our hypotenuse, which is 25, and same with our theta number 2. Our opposite side is 7, and our hypotenuse is 25. Let's just figure out the signs now. According to the cast rule, sine is positive in this quadrant, so we're going to leave this guy positive, and only cos is positive, therefore sine is negative in quadrant number 4, and so we're going to add a negative sign, and we're done.